You are floating far from everything, in the quiet dark between the stars. Out here, time feels normal. Seconds tick by on your watch, just like they do on Earth. But Einstein's theory of general relativity says that time is not the same everywhere. Mass and gravity bend not only space, but time itself. The stronger the gravity, the slower time runs for anything caught inside it. So imagine a simple experiment. You keep one clock with you, out here in weak gravity, far from any massive object. And you send another clock down into a deep gravitational well near the surface of a neutron star, or deeper still, into orbit around a black hole. From your point of view, the clock in the strong gravity will appear to tick more slowly than your own. From the clock's point of view, everything feels normal. Its seconds feel like real seconds. It is your clock, far away, that seems to be racing ahead. This is gravitational time dilation. Now take that idea and push it to the extreme. Instead of a neutron star, place your second clock on a safe orbit around a massive black hole. Not crossing the event horizon, not falling in, just hovering in a stable path very close to the edge. Then imagine you are the one on that orbit. You, your ship, your heartbeat, your thoughts, all running at a slower pace compared to the distant universe above you. The question is simple but strange. If you orbit a black hole long enough, could you watch the far future of the universe play out in fast forward above your head?
To explore this, we need a very particular black hole. It has to be supermassive, millions of times the mass of the Sun, like the one at the center of our galaxy. Near a small black hole, the tidal forces would rip you apart long before time dilation became useful. But around a supermassive black hole, gravity is strong enough to slow time dramatically, while the difference in pull between your head and your feet can still be survivable at certain distances. So picture a safe orbit, just outside the region where you would be torn apart, but close enough that gravity is doing serious work on time. From your point of view, you are simply falling forever, missing the black hole at every turn. Your ship circles the dark center again and again, following a curved path set by the geometry of space-time itself. Outside your window, you see the black hole's shadow, a perfectly dark disk wrapped in a bright, swirling ring of light. The accretion disk glows. Jets of radiation may shoot out from the poles, and the background stars are bent into arcs by gravitational lensing. Inside the cabin, everything feels ordinary. You breathe, blink, move your hands. You can pour a drink, write in a notebook, check the instruments. Your personal time ticks forward at a normal rate. But the navigation computer shows something unsettling. Compared to a clock far away from the black hole, out in interstellar space, your seconds are stretching. Maybe every hour you experience is 2 hours, or 10 hours, or even more for the outside universe. You are not just orbiting, you are sliding sideways into the future. What would you actually see if you stayed there and watched the sky? At first, the difference might be subtle. Stars above the black hole seem to drift a little faster than you expect. Clouds of gas in the inner regions of the galaxy shift their shapes over hours instead of years. Over longer stretches of your time, the effect becomes dramatic. Suppose you orbit for a few years on your own clock, close to the event horizon but never crossing it. When you left, the Milky Way looked pretty much like it does today. When you return, millions of years may have passed for the rest of the galaxy. Stars that were young and bright when you departed have already burned out. New generations of stars have formed and died. Entire clusters have shifted their positions inside the spiral arms. If you stayed even longer, tens of thousands of years by your own experience, the difference would grow. From your perspective, the slow evolution of galaxies begins to look like a sped-up movie. Faraway galaxies drift farther apart as cosmic expansion stretches the fabric of space. Their light grows redder and dimmer, shifted into longer wavelengths as the universe expands. The background glow of the cosmic microwave radiation fades and cools, slipping into wavelengths your eyes can no longer see. Up above the black hole, the universe is aging quickly. Down here, in your tight orbit, your body is only a few years older. From your point of view, you have watched the future unfold at an accelerated rate.
This sounds like science fiction, but the core idea comes straight from relativity. Time dilation near a black hole really does mean that less time can pass for you, while much more time passes for the distant universe. However, there are limits. You cannot simply sit in orbit and watch all of eternity. The environment near a black hole is not gentle. There is radiation from the accretion disk, cosmic rays, and the constant threat of tidal forces and instabilities in your orbit. Your ship and your body can only survive for so long. The black hole itself also has a lifetime. Through a process called Hawking radiation, it slowly loses mass over unimaginable timescales, eventually evaporating away. By choosing the right orbit and the right black hole, you could jump far ahead in cosmic history, but not to the very end of time. There is also a deeper subtlety. From your perspective, you are simply living your life, one second after another. From the perspective of someone far away, watching your ship orbit the black hole, your time appears slowed. Both views are correct within their own frames of reference. Relativity does not give us one absolute universal clock. It gives us a web of local times, all stitched together by the geometry of space-time. So can you watch the future of the universe from a black hole? In a sense, yes. By orbiting close to a massive black hole, you could let the rest of the cosmos race ahead of you, then return to find that the universe has changed far more than you have. But you would not be a detached observer outside of time. You would still be living inside your own timeline, aging at your own pace, paying for the journey with every second you experience. Black holes bend light, they bend space, and they bend time. They do not just stretch our understanding of physics, they stretch our understanding of what past and future even mean.